The autumn chill brings the same loud dispute to the meadow every year. The jays aggressively claim that forest nesting birds fled the early frost in far greater numbers than meadow birds. The sparrows vehemently disagree. The problem with resolving this argument is the nature of the data. The facts being debated, where a bird nests and whether it migrated, are categories. They are kinds of things, rather than standard numerical measurements like temperature or wingspan. Enter the magpie clerk. To settle the noise, she acts as a neutral auditor, initiating a census of exactly 60 birds to gather raw, qualitative data. She asks each bird 2 distinct questions. Neither one is a number. First, where do you nest, forest or meadow? And second, did you stay or fly south? To turn these qualitative traits into countable proof, we need a specific organizational tool, one designed exclusively to handle non-numerical categories. This is a two-way frequency table. Rows track the nesting question, forest and meadow. Columns track migration, stayed and flew. The rule is strict mutual exclusion. Each subject lands in exactly one cell. The joint frequencies settle. 12 forest birds stayed, 18 flew. 20 meadow birds stayed, 10 flew. The margin totals act as a required system audit. 30 forest birds plus 30 meadow birds equals 60. 32 birds stayed plus 28 flew equals 60. The count is clean. The table perfectly organizes the chaos of the meadow into clear raw numbers. But these joint frequencies are only the starting point of the analysis. Looking directly at the cells, the jays immediately declare victory. 18 forest birds flew compared to only 10 meadow birds. But relying on raw absolute numbers is a mathematical trap. Counting how many only works as a fair comparison if the 2 distinct groups you're looking at happen to be the exact same size. To find out if a forest bird is actually more prone to migrate, we have to calculate the relative frequency. We need to convert how many into how likely. We do this row by row. Out of 30 total forest birds, 18 flew. Dividing 18 by 30 yields a 60% flight rate. Now the meadow birds. 10 flew out of 30. That yields a flight rate of roughly 33%. Converting absolute counts to row-by-row relative frequencies normalizes the data. It creates the only honest baseline for evaluating groups against one another. Look at these 2 rates side by side. 60% against 33% is a stark mathematical disparity. In bivariate categorical data, an association exists strictly when the rates between rows behave significantly differently from one another. The real-world implication here is concrete. Knowing a bird's nesting location genuinely alters the statistical probability of its migration. If those rates had been mathematically identical, it would prove the null hypothesis, meaning nesting ground and migration choice had absolutely no relationship. The substantial gap between the 2 rates definitively settles the dispute. Proportional logic succeeds exactly where raw numbers fail. The argument ends without another ruffled feather, and the subjects peacefully disperse, mixing back into the autumn sky. Yet there is a vital statistical limitation to this exercise. While the two-way table proves that these 2 traits travel together, it completely lacks the capacity to explain why they do. Do forest birds migrate more frequently because of a thinner canopy or colder hollows? Those are external variables that fall completely outside the table's scope. Evaluating categories requires a disciplined procedural flow. Organize traits into a single grid, audit counts using margin totals, then calculate rates row by row. Raw counts only begin the story. Relative frequencies finish it. And responsible data analysis never claims more than the numbers can explicitly prove.